Swayam Prabha. Digital India. Educated India.
So, okay, welcome back. So, what are you going to start today are turbulent boundary layers. Okay. So, to sort of grasp all this, I think a basic knowledge of boundary layers, laminar boundary layers is necessary. So, I also have another NPTEL lecture called Introduction to Boundary Layers, and of course, there are other sources on the web. You can look at those, and I consult Schlichting's book. Okay, so you'll need to sort of know that in order to grasp all this. So, but I'll just sort of, I won't be able to do any details of that in this class, right? However, I'll try to, some basic concepts and understanding of boundary layers is necessary to sort of, grasp this material. So, you'll have to do that sort of study. Okay. All right. So, essentially what we're going to talk about today is turbulent boundary layers. Okay. Right. So, essentially let me see how I can explain how this is different from a laminar boundary layer. Okay, let me draw two pictures here. Okay. So, I am going to draw the boundary layer over a flat plate, which is the typical thing to do. So, say I have okay, let's just okay. So, I have a flat plate. Okay. Let's just do this here. Same thing, I have another flat plate here. Okay. And there is an incoming fluid flow. So, in this case, let me draw axis system. Okay. I have a fluid which comes in. Okay. This is my incoming free stream, right? Okay, so let's just say this is the laminar case. So, I'm going to actually use this space. So, let's just say this is the laminar boundary layer, right? And this is the turbulent boundary layer. Okay. Now, what happens in the first case, laminar boundary layer? So, I think we'll draw that typical. So, we'll draw this, right? And what exactly is happening here? Well, there is flow here, there is flow here, there is flow here. Right? Flow is happening, right? But what is different? I mean, so you had the free stream which came in here, but then there was no flat plate. Now it's encountering the flat plate. I've drawn this green thing, but this is the demarcation, right, of the boundary layer flow, right, which is here, and this is dominated by viscosity, and a little distance away from it, it's again just a free stream where the effects of viscosity are negligible, minimal. So, we can ignore that, we use potential flow to solve that. Okay. So, what is the difference then? It came in like this. So, this was a velocity profile that I have drawn here. How would this look like? So, let me sort of erase these things. Okay. I am going to erase this and okay. So, anyway, these are the basically the free stream. Okay. All right. Now, let us just say we take a couple of locations. Say I will take these 2 locations here, right. So, this is say location say x 1, this is location x 2. How will the velocity profile look like? Okay. So, then the velocity profile, well actually what happens to the flow? What happens to the flow is, for example, this streamline that you see here, the first one, right. What happens to that here? Well, it does not move at all, it comes to a stop. The flow which is nearest to the solid obstruction here, which is the flat plate, right. The fluid which comes in contact with that, that will come to a stop, and that is basically because of the viscosity. So, there is no velocity a component here. So, this actually is 0. The next one, so this is almost like the fluid is moving in layers, one layer of the other, but each layer is moving in with different velocities, which is not the case if you see the free stream. The free stream all has the same velocity, but this is a concept now. The moment it encounters the flat plate, right, the viscosity property, the viscous property of the fluid becomes dominant, right, for the fluid in a distance which is very close to the surface, and this is that distance, or this is a region in which the viscosity is dominant, and that is essentially your boundary layer. Okay, because beyond that, again the flow it will be simply like the free stream here. So, I could actually for example over here I would actually be able to draw a free stream something like this, which is also I've drawn smaller vectors. Actually, it should be the same size. So, this is also actually a u infinity. So, it is right here, you will actually these should all be of the same size. Okay, please mind that. Okay, so, this is also u infinity. This is not to scale. Okay, let us just say this is not to scale. Well, okay, this is not to scale. Okay. Now, so similarly here when I come here, so what happens is this green line that I have here is a demarcation between the free stream and the boundary layer flow, right. So, I would think that around this place again I get back the free stream. So, till that, so okay, so this is about that. Okay, this, and finally this. So, this is almost like it's almost like that, something like that. Okay. Okay. So, similarly you have that here. Okay. So, something like that. Okay. So, at x 1 and x 2 you have these boundary layer profiles, where here actually it is again right here it is actually u infinity, right. And at every location therefore, now how do I calculate the height? That you can see that. So, I keep moving such that finally I am able to, because here if I measure the velocity is going to be 0, right, like at the wall, here it will be 0. As I keep moving up, right. So, as I keep moving up, so I keep moving up till, right. So, in the sense that this green line is not a solid or it's not a real sort of boundary in the physical flow, right. This is only for our illustration here. Okay. So, in the sense, so that you can just keep moving away from in the y direction, you keep moving there, and we reach a height where it is just about u infinity. So, the typical description is like 99% or whatever. So, now I mean that is really a description up to you. So, which is essentially you get back the free stream. So, till about that time what the distance that you have, so that is your essentially your boundary layer and we denote that height by this. And as you can see, that height is different along x, right. That the height along x2 is, say, so we will just write that as this. It is a function of x. So, you can see that because that height is this, right. So, therefore, this is so this delta x is nothing but your boundary layer thickness, that is the boundary layer thickness. Okay. So, essentially here we are looking at a flow which is moving in layers, and this was typical Prandtl's boundary layer theory, right. And so this is, I think, your kind of, this is a very basic description of how boundary layers should be. Boundary layers are how we sort of start studying. This is a typical laminar boundary layer. Okay. Let me write out some equations, and then finally we will move on to the turbulent boundary layers, right. So, these, right, you have a delta x, right. So, delta is your height. So, delta is also going to be, you have an expression for that. There is something called a boundary layer displacement thickness and boundary layer momentum thickness. Okay. Now, I will briefly describe that. So, essentially what happens is that you can see this if you take a control volume, right. If you take a control volume which is encompassing this, right. So, let us just say this is your control volume, right. Actually, this top, okay, this AB, right, will make it coincide with the green line. Okay. Just think about that. I am going to just leave it like this for the moment. What I want you to just see here is that the flow coming in through AD has the kind of profile which is u infinity, which is a uniform velocity profile along y, right. But clearly at BC that is not the same, right. So, if you say what is the momentum which came in, what is the momentum that came in, yeah. So, that would be mass into velocity, and how would we care? So, there is a certain difference in this momentum, is not it, at AD and BC, right. So, therefore, if I took just this height, so let us just say this height is h, let us just say this height is h, okay. Let us just say this height AD is equal to h. Okay. So, if BC is also equal to h, I am not going to get the same momentum, because if you see here, right, okay, when I am talking about BC actually. So, if I took the boundary, if I took the AB to some match with this green line, say, right, then my h would be same, right. So, I would basically say this h and this h. So, the same height is not going to give me the same momentum across that boundary. So, essentially what I am trying to say here is the boundary at, say, the right hand end of your control volume, which is, say, BC. Now, that needs to account for an extra height above this, right. So, which will give me a difference between the momentum which came in, because this is a velocity which is u infinity throughout. It is a uniform. Here it is not. Here is u infinity only at the top, and etc. is very small. So, therefore, I am going to have a deficit of momentum, right, which is going to be transferred, and that cannot be allowed. Momentum has to be conserved, right. So, therefore, we take a height across, in the y direction of the fluid, right, where the velocity will be the free stream, and if I add that to the velocity, the momentum across the velocity profile here, then that should add up. Right. So, that extra height is what is called as the displacement thickness, right. So, that I can sort of, let us just say that height is this, and I am going to call that, so that height is actually called, and as you can see, that height is also a function of x, it is also a function of x, right. So, actually that is not the, sorry, I wrote momentum thickness is that, but I wrote this is not the momentum thickness, we write as this. Momentum thickness we write in terms of this is how we denote, this is the momentum thickness. Okay. So, theta is essentially in this case, so theta Okay, let me write it here. Okay, so theta is essentially momentum thickness, okay, of a boundary layer. Now, so this is, we conserve the momentum, we also need to conserve the mass. So again the same concept, right? If you see the mass which is coming in at say AD, it's not the same mass which goes out of BC if I take this velocity profile. So I need an extra height, right, and that extra height will give me back the total mass that is coming in, right, account for it. So that height is actually called the displacement thickness, and that is a displacement thickness. Let me not sort of, this is also dependent on x and this is also dependent on x, the momentum thickness, as you can see, right. So this is your boundary layer displacement thickness, right, and these two are not equal, these two are not equal. Okay. So, okay, so that basically that. Okay, so then I can write, you know, using basically using that concept itself. So I can write out the expression as, so so delta star, right, the displacement thickness is, so we take some height in this case, you know, so let's just say we'll take some height, right. So we'll take some height, and that height, so u, right. So this this velocity here, it is denoted as velocity profile. So that is denoted as, right. So this component which is in the x direction, right. So that is going to be that u by u infinity into 1 minus, okay, I made a mistake, sorry. Okay, so essentially 1 minus rho u by rho infinity u infinity dy, okay, and theta x, which is the momentum thickness, is again to h naught, is essentially u by u infinity 1 by right. So I think I've, you know, kind of briefly covered everything. Now the question is, how does this description of the boundary layer moving in layers change, and how do I sort of change displacement thickness and boundary layer, I mean the momentum thickness, how do these, how do I redefine these things to account for turbulence, right? How do I sort of do that? Well, I think the picture remains exactly the same. The picture remains exactly the same, except for, let's look at this. So what we will do is exactly what we've done earlier when we started considering what a turbulent flow. We basically said the turbulent flow has a mean flow, right. What changes here is, so this bit, right. So let me just write that, that is your mean flow, right. So this is the mean flow, which is superimposed with a turbulent with a fluctuating part, right. So this fluctuating part is nothing but right. So if you compare this to the boundary layer, laminar boundary layer, essentially what here the incoming flow is essentially the laminar free stream, right. And what's coming in here is a turbulent free stream, that's all, right. Turbulent free stream, which I represent as a mean value, right. So then essentially what I'm saying is, okay, let's just write it like this. this, oh well, actually no, what I did was correct. That, yeah, what I did was correct. So, with that I superimpose the, well, you know, I could actually, in this case, this, okay. So, we are going to consider, you know, a 2D scale. So, that essentially what we are going to say is, so if when I say 2D, what does that mean? Okay, let me just take a minute and say that first. When I said 2D boundary layer, what does that mean? That basically means the picture that you are seeing here, right, you will see the same picture at different distances away from the plane of the board, right, plane of this computer screen here. I am writing on a computer screen. So, I take different distances, right, I take different distances away from the computer screen, and you see the same thing, which is what is happening now, right. So, therefore, I see a 2D picture. So, if I took another, say, if I took a mirror, for example, right. So, I would see the same thing on the mirror, whether I kept a mirror here or here or here or here, or you take a transparent piece of, you know, a slide or something, you know, transparent piece of material, and you look through it, you will see the same thing. So, you see the same thing at distance which you take away from that. So, if this is your z direction, and in that direction you see the same thing. So, that is why it is 2D. Now, 2D, and of course, in the boundary layer case, it has been experimentally proven that the v component of the velocity is negligible. Its effect on the boundary layer is negligible, that is all. Okay. So, that is why the only velocity component which becomes dominant in the, you know, the boundary layer studies becomes the actual component of the velocity. So, essentially the velocity, okay, the free stream, okay. So, the free stream is all this. Okay, I have to sort of write that a little differently, isn't it? Okay. That, right. Now, we get rid of that because of 2D, right, and this one is negligible. Negligible essentially in boundary layer flows, that is all, and that is experimentally proven. So, therefore, we are left out with this. So, that this is what we are considering. Okay. So, in that context, so what you have here, so therefore, this v infinity or u infinity, the total velocity, total free stream, therefore, right, now you consider that as a, so this one, right. So, you can say, this is your, so therefore, when I say u infinity in here, which is the u infinity here, it's the same thing as the total incoming free stream, right. Okay. So, now coming to the turbulent boundary layer description here, okay. So, I have this mean flow, right, which is denoted by these blue arrows, and I write that as a mean flow. Along with that, this is the fluctuating part, right, and this whole thing then is basically equivalent to the free stream, right. Free stream, you know, essentially that, which is this, right. So, essentially the free stream now, the dominant free stream is essentially the axial component or the component of velocity which is in the which is right along the flat plate, you know, that is your action, you can consider that as an axis. Okay. So, that is my, so now that is the case, right. So, then what do I do? You know, I again have to redefine, I have to define. So, let us just say, what color should I, you know, what color should I take? Okay. This is my boundary layer. How does that change? Okay, what is going on here? Okay. So, I would think so now the point is, how do I redefine the boundary layer displacement thickness, boundary layer thickness, displacement thickness, momentum, I mean how what do I do, right? Well, what you do for the turbulent case is essentially this, right. The definitions all remain same, definitions all remain same, except this is the difference. Okay. So, like I said, how do I calculate the delta x here? The delta x, which is the boundary layer thickness, is how I calculate that. I start from the plate, which is y is equal to 0. I keep moving away with y increasing. I go till the velocity, which was 0 at the wall, at the plate. It increases slowly, and finally, I reach the free stream, where I am getting back the full free stream, which is u infinity. Otherwise, it is a fraction of the it is 0 at the 0 at the wall, and it is less than u infinity between that, okay, within delta. So, in this case, and then we basically, this is a very typical description. So, essentially it should get back about total of it. So, essentially so in here, so u infinity, this u y, right. So, at y is equal to 0, right, which is the flat plate, right. So, u is 0, right. Now, at y is equal to delta, u infinity is this free stream, right. So, typically we say that this is how much is, this is just about, how much is about, well this is, which is this. So, essentially we say this is about 99% of this. So, you have almost reached it. This is how we typically write it. Now, in the turbulent case also the same thing. So, here the way it changes now. Okay, now let me demarcate this. This is a discussion. Now this discussion is essentially for the laminar case. Okay, and what I am going to write here is for the turbulent case. Okay, now again, so here at y is equal to 0. So, I will have a velocity profile here also, right. So, that this thing, and y is equal to delta x, right. U y is 99%, right. So, at which the okay is, so let us just say u y, okay, u y is 99% of the free stream, total free stream. Okay. So, you are like, how is it different? It is not, it is not. What is different is how you define the u y now in the turbulent case. So, in the turbulent case, this u y is again, so if I draw, so let me draw a velocity profile. How will the velocity profile look like? Again, I will just draw one here. Okay, I am going to exaggerate it. So, again the velocity profile here, I am just exaggerating this. Okay. Okay, this is my velocity profile. Okay. So, this is the velocity profile here also. This is turbulent velocity profile, right. If that is the case, so therefore, in here, so this u, so I have a certain u here, but you can see there is a little difference between the u value here and the u value here, right. So, what, so this u is nothing but the mean velocity. So, then we will take the mean of this, right. So, this u y, so we will essentially take this one, okay, that is equal to mean value, right. right, because now that will depend on at which location of x and throughout your y, right. So, the thickness is defined as the height, right, at which the mean velocity in the x direction, the mean velocity in the x direction, which is this, right, is equal to 99% of the free stream. Okay. So, essentially that is the difference. So, this is, so what you do is take the mean in the x direction, that is all, right. So, x and y. Okay. So, therefore, how does my equations change? Okay, let me write that down. So, then my delta displacement thickness, okay. How do I change that? Again 0 to h naught is 1 minus rho by rho infinity, and all we have here is u mean, right, that is the difference, by u infinity T y, right, that is the difference. So, you can look at the difference between the laminar and the turbulent case. Okay. And the other one is the theta, right. So, again theta is equal to, okay. So, it is u mean by free stream 1 minus u mean right. So, the same thing, right. So, okay. So, this is, so the everything here is for the turbulent boundary layer case. Okay. So, that is how you sort of redefine for the laminar case and for the turbulent boundary layer. Okay. The question that I am going to ask you here, ask or sort of, yeah, I guess I am thinking aloud, is that do you like the description? Do you think this is okay, or you know, you are a little confused? Well, I have my little doubts here, because when I am considering a laminar boundary layer, the basis of that is that I can think of the fluid as layers, and then each layer moves over the other, right. Now, the moment I say turbulent behavior, immediately that description of the fluid goes. There is no layers or anything, right. It is turbulent now, right. So, then how does, so all this description that we came up with, the, you know, the boundary layer thickness, momentum thickness, displacement thickness, etc., and the very fact that we have velocity profiles like this and we go along the x, etc., does that still hold in something like this, right? And how, you know, is that boundary layer theory is going to be useful in, you know, that same boundary layer theory for laminar boundary layer theory, can it just be used here as well in the same way, except that when I consider the velocity here, it just, we just take the mean components of the velocity, right, and the boundary layer thickness is essentially when the mean velocity reaches about 99% of the free stream, right. So, how is it that will that hold, or is that wrong? Okay, that is a question I would like to sort of pose at this point of time, okay, and hopefully we will answer that as we go along, but let us think about it. Okay. All right. So, so there are different as you can see, we've described, or we've come up with several lengths, right. You have the boundary layer thickness, displacement thickness, momentum thickness, and of course, the length, the axial length along x, right. So, in that, and then the flow is happening, right. So, then we should be able to discuss several different types of Reynolds numbers, right, because now what do these things depend on and how I am going to calculate that, and etcetera, etcetera. I think those are questions which we will need to answer, right. So, I could have sort of describe say various Reynolds numbers, right. So, you could have of course depend on length, right. So, that is nothing but some distance that you could just define that based on the boundary layer thickness, which is nothing but and do you see that if I let me just finish this and then we'll discuss. So, let's write this out first. Boundary layer, it could be displacement thickness also, right. And then momentum thickness, So, as you can see here, So, as you can see the REX, right. So, that will change, right, as you increase the x, right. So, similarly all this Reynolds number is going to change depending on your boundary layer and the location. I think that is an important thing to see here, right. So, whether the theta, right, whether the theta, the displacement thickness etcetera, these will depend directly on the Reynolds number. The local Reynolds number is something that we will have to see. Now, now the point is, when will we encounter, when exactly will we encounter turbulent flow? I mean, we are talking about flow over a flat plate, which is laminar, right. Now, why are we even talking about turbulent boundary layers? Why is it that will we have turbulent boundaries? What do I mean by that? Well, what we mean by that is that this same boundary layer, you don't need to do anything to it, but it doesn't. So, when you study the stability of boundary layers, you will realize that the boundary, you don't need to do anything to it, but that is not going to be a nice little formation of boundary layer throughout. After a certain time, because you see these Reynolds numbers, if you see these Reynolds numbers, these are changing. So, there will be a time when there is a certain critical Reynolds number, after which, around which, right, the flow reaches, this is a critical Reynolds number, around which time it transitions and then it becomes turbulent, right. So, if you keep having the flow along a flat plate going, then it is not going to continue for eternity. That is not going to happen. So, the reason for that being these Reynolds numbers, right, as you can see. So, of course, so let us just say the effect of the pressure gradient is 0 at this point of time. I am just talking about the viscous nature, dependence on Reynolds number actually. So, if I may make sort of a note on that, let me write a note on that. Now, so in a boundary layer, over a flat plate, say, so we are not considering any the effect of pressure, right, on the flow. So, I am just talking pretty much just about the viscosity, right. So, dP dx is 0, it is not accelerating or anything, it is just uniform. So, that is important. What the point is, it is not doing anything, the external flow is not accelerating or anything. So, at some location x, say from the leading edge of the plate, Rex, right, is critical. You can see that, right. So, Re is constantly increasing, right, if you increase the distance, right, critical, which is about 1 million, right. So, this means it leads to start of transition, right, and followed by flow becoming fully turbulent. Okay. So, that is what we mean by the critical Reynolds number. Okay. All right. Now, the mean momentum equation in the y direction. Okay. So, let us see what that is. Now, mean the mean momentum equation in the y direction is okay. So, then we take a we integrate this, right. So, we integrate so what we get is so let us just say this is the integration constant. Let us just say it is P w. Okay. Now, let me first talk about that and then we will discuss some more on that. Okay. Now, this okay, let's go back to the previous page. Okay. Now, this P w that I have written on the right hand side, okay, this P w, okay, what is that, right? The mean pressure at y is equal to 0, right, at y is equal to 0. So, essentially, so in this case, which is the which is on the axis of the flat plate, which is on the flat plate basically, right. So, P w x is essentially P bar, which is the mean P, right, at that particular x, right, at y is equal to 0. Okay. So, essentially this one, okay, so this essentially means what? Means y is equal to 0, which means this is the wall. Okay. So, I can write here is the mean pressure at the bottom of the wall. Okay. So, that is what I have written here. So, it is the mean pressure at the bottom at the wall, you know, this I have written it here, that should be okay. Okay. So, then therefore, dP dx, right, dP dx is equal to so that's why I'm calling it W, which is essentially meaning wall. Okay. So, this, right. So, essentially what this is telling you is that the mean axial pressure gradient, right, the mean, this is the mean axial pressure gradient, right, is ddx of P at the wall, right, which is ddx of P at the wall, right. So, this axial pressure gradient, right, this one is uniform, is uniform, right. So, this I can write here. So, what this essentially is telling you, right. So, the mean axial pressure gradient, right, is essentially the axial pressure gradient of the wall pressure, isn't it. So, therefore, it is uniform here. Okay. So, mean axial pressure gradient, right, is uniform across the flow, if I were to sort of explain that a little bit, what I am trying to say here is, say you take locations, right. Now, so if you took x1 and x2, right. So, essentially dpw, right. So, dpw, right, x2 here. So, dpw at x2, right. This you could write as pw of x2 minus pw of x1 by x2 minus x1. Is that right? Now, this does not depend on the y. You understand what I am saying? Okay, I might as well just write that. Now, so say I have this this is my y, this is my x, right. This is my flat plate. Okay, I have this. Okay. Okay. And then I take, again this is my boundary layer. Okay. So, then I take two locations, one location is here, the other location is here, this is x1, this is x2, right. And we have just said that dp dx, right. So, in this case this is equal to p mean at x2 minus p mean at x1, right, by x2 minus x1, right. So, mean of the pressure at location x2, mean of the pressure at location x1 by the distance between them, that is what it means. And this we said is equal to is wall pressure dd x of that wall pressure, right, which means this is equal to wall pressure at x2 minus wall pressure at x1 by x2 minus x1, right. So, therefore, now say I take the locations here. This is say y1 and y2, and this is say y is equal to 0. Right. So, this dp dx between the two locations at the wall is this, right. So, the pressure gradient in the x direction is equal to this, right, at y is equal to 0. What is this at say y1? It's the same, right, because what this pressure gradient in the x direction is actually equal to the wall pressures, is the difference in the wall pressures, right. Is a gradient in the wall pressures in the x direction, which is so therefore it is uniform, right. So everywhere you go, so y1, and if you go to y2 or to any other at any other y location, this dp dx is not going to change. So, the dp dx does not change. Okay. Now, in the laminar boundary layer, what happens is we basically know that dp dy is equal to 0, right. This is for a laminar case. This is for a laminar boundary layer. Okay. So, and pressure is actually equal to the free stream pressure, right. So, if you have a free stream pressure here, that is going to be imposed onto the boundary layer and it does not change, right. So, therefore, dp dy is equal to 0, right. And here what we see is that the dp dx, right. So, in the turbulent case what we see is that the dp, we will redefine that a little bit better. So, this, right, is uniform across the boundary layer, that is essentially along y. Okay. All right. So, now, so this is something that we needed to talk about. Now, we still need to work on the mean momentum equation in the y direction, some things to talk more on those lines, which we will continue in the next class. Okay. So, I will stop here and take this up again in the next class. Okay. Thank you.